Welcome to Lecture 13 of NCS 507 on Message Passing Interface for Python. So, the purpose of today is to introduce an interface in Python to a standard for parallel distributed computing. So, we will introduce the Hello World. It's another programming environment. And we will distinguish between point-to-point communication and collective communications. So we'll give a couple of standard examples. And then at the end, we will indicate how we will see how a dynamic load balancing method can be implemented. So one lecture is most likely too short to introduce everything that MPI has to offer, but the main point is that you only need a relative small subset of MPI to write very interesting and be productive with message passing. The other point is, and that's still the selling point for Python, is that with a scripting language such as Python, one can get rather easily familiar with the important concepts. So this could serve as a prototype um, to get a feeling of what one can do with MPI. Okay, first of all, again, what is MPI? What is this message passing interface? So it is a specification. So it tells how processes can communicate with each other. There are several implementations. Most supercomputers come already often pre-installed with their MPI implementation. By default here, and of course on free and open source software, we will direct to OpenMPI, so which is an open source implementation of this standard. So one thinks of supercomputers, but high performance computation can also be done on clusters. So in a way, cluster computing also contributed to the spread of the MPI standard. So there is the MPI original standard that is here at the bottom. And then there is MPI for Pi. So MPI for Pi provides bindings of MPI for Python. So what it does is that it provides an object-oriented interface. It is very close to the message passing interface standard. So once you know how to work with MPI for Pi, the step to working for a compiled in a compiled environment, how MPI is used in C or in Fortran or in C++, that step should not be that hard. It's mainly what MPI for Pi can help you with is the introduction into thinking parallel. So how can you manage, how can you organize your computations on a distributed memory computer? So it gives you, you should also not leave the Python world. So we can, so you can send objects, any Python object, via the pickling. So pickling in Python is a serialization of any object, and that can be then passed through an MPI communication. So you do not need to rewrite your software, although if everything is already in terms of arrays and very basic data types, then this of course works as well. So one can also use this in combination of NumPy arrays. So the point being that one can stay within the objects. So we will demonstrate how you can send over, how you can move a dictionary, a Python object from one processor to the other. Okay, so Python also has the memory management. So in learning MPI on C, one has to allocate on all the processors, and a lot of very strange errors may happen if that does not happen. But Python has a much more automatic memory management, also a good exception handling mechanism, and this is essentially again interactive supercomputing. So installing MPI works very well. I installed my latest version with pip. Other distributions may be available. You can find the home of MPI at GitHub. So the current release is fairly recent. Now the drawback of all this is, of course, is that it requires a working MPI installation. So MPI for Pi will not help you with getting MPI installed on your computer, and that might now still be the main stumbling block there. So you have to get MPI itself installed on your computer. All right. How does message passing work? So every process executes the same program. So this is the single program, multiple data. However, does every program then do the same thing? Not at all. So every process, every program has a unique identification number, which is called the rank. And based on the rank, you can decide which process does what. So this is still a very flexible program, but this is still you can do all kinds of parallel computation with this. It is not a limit. But when you compile, when you deal with software, you actually work with one single program. And that single program defines everything. So that doesn't mean that you have to stuff everything in one single file. You can still work with modules, and we can still work with existing libraries. What I also forgot to point out that, well, why would you use an efficient language such as Python for high performance computing? Well, the bottleneck can be compiled code. So you can use Python again as a wrapper. So what the worker nodes will do will be um, will be often compiled code, or it is implemented in NumPy, for example. All right, so this brings me to the bottom line. So there is one single program, and that is often defined in the manager worker model. There is one process, the process that has rank 0, that has the status of manager. So that process will distribute the jobs among the workers. The jobs, this could be in a Monte Carlo simulation, the seed of the random number generator. So it's the manager responsible for assuring that every worker starts with a different seed. It could also be data that gets distributed. If we think of numerical integration, we can think of the bounds of the integration domain that needs to be set for every worker. Then all the other processors, and this should be the processes with rank larger, strictly larger than 0, not strictly larger than 1. So all processes strictly larger than 0, they will execute the jobs. So one single program, typical manager worker model. And then as far as the technicalities of message passing goes, we distinguish between point-to-point communications where there is one process that sends and one process that receives, or there are collective communications where all the processors are participating in the communication. The other important distinction is that we have blocking communications or non-blocking communications. Um, Regardless, the point-to-point and collective, both of them are actually necessary. So it's actually the ORs here are actually, we have all these tools available. So with the blocking, you may have a sender that has to wait till the receiving is done. And of course, the receiver can only do something when the message is sent. So, sending and receiving with blocking messages is a very good synchronization tool. But on the other hand, it's also a source for deadlock. So one has to make sure, and this is you, the programmer, you have to make sure that for every send there is a matching receive. For every receive there is a matching send. The non-blocking send and receive is very useful for dynamic load balancing, as we will see at the end of this lecture. Okay, so in essence, this is programming with the message passing interface. So not that bad. So I will give in this lecture a lot of illustrations of this. Okay, hello world, MPI 4Pi. So there are some fixed instructions that one needs to do at the beginning of every MPI program. And first of all, what does this MPI program here do? Every process will write hello world. Will actually write hello from process of that many processors on the name. So it will also write its name. So there are these three properties or three attributes that you can get from the MPI common world, as it is stated. So every processor belongs to some domain. You get the rank, that's the second command here. You get the number of processors in that domain, and then there is also the processor name. So that's then the name where everything is executed. Okay, so here you see it. So I was running this on one multi-core workstation. So you see the output, but you see also that what is actually happening is that when you run this, and you have to have a running MPI installation, a working MPI installation on your computer. To launch jobs with MPI, you launch them with MPI exec. So you execute an MPI job, and essentially what is actually done here, 3 Python interpreters are launched, and they are both going to run this MPI 4Pi underscore hello underscore world .py program. So again, this is very similar to what we did last lecture when we were using the multiprocessing module. In a way, if you have to do something with multiprocessing on Python, please use the multiprocessing module in Python. Much more simple to do. The purpose of this tool is that you get familiar with the thinking of message passing. So should you use an actual MPI environment, then this will prepare you. This will make the technological shock, less of a pain, especially if you are a Python programmer. So that's this what this is about. So this also is the main hurdle now in the lecture. If you have come to this far, then you have a working Python installation, you have a working MPI installation, and you have run your first script. And it does not get that much more complicated. Um, okay, so I was hand wavingly explaining what the first program did, and again, in a couple of lines essentially, without compilation. That's another important point. So if you are running actual MPI programs, you also have to compile and link. So there is an MPI CC stage that is also still there. And then you often still have to make sure that the MPI CC agrees very well with the compiled code that you're going to run. So this slide here explains the communicator, the operations to get the number of processes and to get the rank of every executing process. So now in the previous script, every process executed the same code, but you can see that with this get rank, you can very easily now distinguish, send more tailored messages, and do more tailored actions, execute only those instructions that are scheduled for one particular worker. Okay, so this brings us then to the point-to-point communication, the sending and the receiving. So this is the most flexible kind of communication. So we distinguish between collective and point-to-point, but with a loop we can take any point-to-point communication and turn it into a collective communication. Here we have the syntax to send and to receive. When we send, we have to give some data. So what is common here is the data. The data is returned by the receive command and is an argument of the send command. We need to provide a destination when we send, and when we receive, we need to provide a source. Optionally, there is the tag. The tag is more optional but strongly recommended for you as a programmer to keep track of the fact that every matching send must have a matching receive. The main point is that data can be any data. So anything that Python understands can be sent and received. So this is the convenience for the Python user. So we don't need to break this up. So here, if we have numerical data, we could also have had symbolic data, but we have integer types and floating point types. We can label them here with A and B. So we send a dictionary through of some data, and the keys in our dictionary are actually helping us to distinguish. So at the receiving end, we actually also see the labels. So this is one complete program again, where there are two processes. So into running this, you have to send this with two processes, otherwise something will go wrong. If you send it with more than two, then there will be processes that don't do anything, because you see the program will only do something if rank is 0, if rank is 1. Okay, so this is a very flexible program. So if you have to do this in a compiled language with MPI proper, you will need to define the more basic types. So you have to define your types. You have to work with the sizes as well. So there's a lot more involved if you do the actual MPI programming. We have our pleasingly parallel computation. So the Monte Carlo's estimation of the uh, pi by throwing darts. So we are we are generating random numbers in the first quadrant, and we count the ones that are falling in the unit circle. And every one that is in the unit circle, so less than distance 1 from the origin, we count as a success. And the ratio over the total number of samples, so the number of successes over the total number of samples multiplied by 4, gives us an estimate for pi. We are going to first do this with two processors, so just to check the correctness. In a way, this is a modification of the previous program, but now some actual computation is done by one worker. So this is done for 10 million samples. Here the sequential program. Yes, so there is no distinction, there is no sending and receiving. Although, wait, so here you see the setting of the seed. So this is the test program to estimate pi. Then we have the point-to-point communication. So if the rank is 1, so both process 0 and process 1, they compute. So the code that was on the previous slide is actually done before the sending. So here there is no, so they are using their rank as the seed. And that's the main point here. So there is communication at the very beginning. So when the system starts up, every process gets their rank, and with that they initialize the seed. When everything is over, there is a message that is printed. So this is still Python 2 here, I'm sorry. So there is a message that is printed. So this is still interactive parallel computing. We have an easy check on whether that is correct. The process 1 sends the result R to the node 0, who receives it. So you see the confusion here. So there is one single program. Both programs have R, but the R that comes from process 1 is renamed S when it comes to process 0. So process 0 has two numbers, the R that it has computed, and then the S that comes from process 1. So you see, the purpose of this script here is that it allows you in an interactive fashion in a familiar scripting environment such as Python to become familiar with the problems of message passing and in general of parallel computing. So you work with one single program, but the variables in the program mean different things to different processors. So that's kind of the point here that can be illustrated. So there is an R and there is an S. And you see what happens, we have a more accurate approximation than for pi. Here you see what it gets. So I multiply now by pi by 2 because the approximations that are computed are approximations for pi over 4. So we are averaging two approximations for pi over 4, but are just add them up, that gives me an approximation for pi over 2, and then I double them. So that's what the root did, and that's what you see here. Okay, now we know how to do it for a manager and a worker, and both manager and worker did computations. So now let's do this for any number of workers. So the beginning is still the same, but now the collecting of the results is more involved. So there is an explicit loop here, but there is also an implicit loop. So every process that has rank not 0, larger than 0, will do this send. So this is important here in the thinking, in the parallel thinking, where we have loops that are constructed by the running of many processors, by the launching of many processes by the MPI system. So the tag here is 11, so you could think that simply by counting the number of sends and the number of receives, you would be thinking, but hey, I have a loop here, and now it's important that we start with 1 in the loop, and we go to the size, which is the number of processes in this entire script. It's important here that simply counting, you would be thinking, well, here I have size minus 1's receives, and I have only 1 send. But the send is executed by every process with rank larger than 0. So this is an indication again, and this is in a high-level language as Python, that demonstrating the correctness of parallel programs is a lot harder. So one has to recognize that there is an explicit and an implicit loop. Okay, so there is also a running here. So the manager receives one after the other the results from the worker nodes. I call this still here S, but then the S gets summed up in the result. And there is an averaging that is happening. So what the manager will do, it will average the sum and then multiply that by 4 to get an approximation for pi. Okay, and you see that that one can experience quality up. So here I took the number of runs still at 10 million, but then every worker does the same 10 million of samples. So you can see that here, and this was done on a 12 core, so you can actually go with 64 processes. And gradually the accuracy improves. So you can check the number of decimal places that agree gradually. So in some sense, I didn't leave off the timings, but it's more quality up here. So it is effective. Using more processes gives you a more accurate approximation. And the time should roughly be the same, although on a 12 core with 64 processes, it probably took longer. Okay, in essence, we have almost seen most of the operations, the send and the receive. There are collective communications. The collective communications are provided with specific operations in MPI. Why use them? So there is the broadcast to send one number to, or one data. So here we are going to send a dictionary with the approximations for pi and e. So this could mimic the initialization of constants at the very beginning. So if we are doing this, we could have used the send and receive. Why don't we do this? Well, first of all, with the send and receive, we have this deadlock that can happen. The other issue is that the system may have a much more efficient um, efficient algorithms for broadcasting. So there is the um, broadcasting where process 0 sends to 1 first in the first stage, then 1 has the data as well and sends then to to other to another process while 0 continues to send. So there is this fan out broadcast. And one can do this with logarithmic cost instead of linear cost. So this is a topic for a high performance computing class. We are not going to get in here. The point here is that the broadcast is just one single instruction, and everybody takes place in this. So here there is still an if else, and that is to define the data. So the data actually must be defined as a name. So there is this initialization here that must happen. Because the data is the input element as well. And it is important that there is no if. There's no if in front of the broadcast. Everybody executes this command. And the one who broadcasts is the root. So these type of broadcast operations also will work from any node. But you have to indicate who is the sender here, who has the data, and who will broadcast all the data. Another collective communication is scattering. So scattering means that you have an array of data and you want to scatter the data among all the workers. Again, this is a collective operation. Here we have the outcome of a function, I plus 1 to the power 2, that is scattered to all the processes. So you see, if you evaluate this formula, the worker nodes or all the processors, so this was done with 10 processes. So 0, if you evaluate this, evaluates to 1, 1 evaluates to 4. So in some sense, this is the evaluation of a function. That's done via a scatter. Again, it is interactive computing. On a true supercomputer, you may not have this luxury that you can do this interactive computation. So you can do this on your own computer with a limited number of processes and check whether the logic of your programs works, whether the communications are not going to result in some deadlock. The program fits in one slide again. The difference here is that we have now a list that is scattered. So in order for the scatter to work, you need to have something that has an index, that is indexable. The data consists of numbers, but I'm almost sure that the entries that are in that list can also be of any Python type. So this is also very flexible. Then the mirror of the scatter is the gathering. So the gathering is very useful in a computation where the root node wants to collect or to gather, wants to collect all the results computed by the workers. Again, there is one single program and there is one data structure. So there's one array, and the array exists within the namespace of the program, but the workers are going to fill out only one portion. So here you see the gathering. Everybody participates in this gathering. And now the data is one element. So the data is gathered, and the data here is gathered by the root. So at the end, the root node has all the data. So this is the mirror of the scatter, where there is a test that at the beginning the root node, or the one who initiates the scatter, has to provide the data. Here it's the opposite. Perhaps the picture will make it a little bit clearer. So here we have, say we want to process some numbers, only 100 numbers, not so realistic. But you have, or perhaps it is realistic if the computations on these numbers are very intensive. So here you see the scattering, and everybody participates. So at the end, there is actually data movement happening from the root node, P naught here, receiving data, the first 25 numbers. And then there is the gathering, assuming that what the processors did was doing something with these numbers. And then the sums are gathered to the root. So the root node has also this array structure. So the array structure is available, is defined in the namespace somewhere of all the processors. But the processors, the workers, so the processors with rank higher than 0, the workers are only using one location in this namespace. Here is the simulation, or the prototyping, if you have to do this with Python. So this program has still a lot of use because you do not have to think about the allocating and the deallocating and the indexing. So here is another terminology. It's kind of, you have data and you slice it up. Data parallel programs work like that. So there is data parallelism, where workers compute on different parts of the data. So they first need to have their slice, and then they have to return what they did with the slice. So here is just the sum of the numbers. Okay, here is the first stage. So there is the scattering. And now this is done with the send and the receive. So it is communicative data, where we are going to sending the slices, we're going to distribute the slices in a point-to-point communication. So the exercise will then to be using the scatter and the gather. So this is the scatter stage. Explicitly done, we compute a slice, and we are sending these slices now through with a type. We are sending the MPI integers through. So we are indicating that they are MPI. So we are using NumPy, where we can also provide the type. Our type are integer numbers. So in the sending of the slice, we can also indicate that we are doing MPI integers. It might be that everything is optional, and in some sense this contradicts what I said earlier, that types can be anything, also dynamically typed. But this is a good preparation also for going on to a lower level, where computations are typically done on arrays. So this is again in the prototyping mentality. So then the actual computation is calling sum. That's a built-in function. You could also call here one of the libraries. And then we do the point-to-point receiving, where here you see that the sums is initialized. So there is a sums, every process will do that. Every process will actually have sums there, but that will be allocated to 0. In this receiving end, the root node will do the receiving. So this is still a collective communication. So there is the implicit loop. So every process with rank strictly larger than 0 cents, and there is the explicit loop, where source and destination must match up. Okay, so something subtle. Python is case sensitive. So if you are working with little case, no type declaration, work with uppercase in the send and receive. You are supposed to be using type declarations. Rather subtle. Okay, so I have 10 minutes left for a more realistic application. So in pleasingly parallel computations, we assumed that the amount of work per process is the same. And here you can see that this is rather unrealistic, so it could go terribly wrong if you're going to distribute. So you have even numbered jobs. So here we have 8 jobs. You see that the even numbered jobs, so job 0, 2, 4, and 6, they are long jobs. If they arrive or if they are staying at the root node, then worker 0 will have to work at least twice as long. Whereas the odd numbered jobs, job number 1, 3, 5, and 7, these are short jobs. So in a static workload distribution, worker process 0 will finish quite quickly. So you will have this workload imbalance. Now in a dynamic work balancing, it is done as here, and the example was specifically contrived so that the sum of a small and a big job, they add up to the same. So there is this nice balancing that happens. So if a worker is done, it's going to request the next job. So you have job number 0, job number 1. Job number 1 is done by worker 1. So they start as in the static workload. But worker 1 is done and requests the next job. So the next job has index 2. So it's an even number of jobs, it's a large job. So worker 1 gets then the large job. Worker 1 is still busy when worker 0 stops, and worker 0 then gets a small job because we are still at the even. Yes, we are at the even jobs. The next job is then job number 3, which is a small job. How does this work? So we will simulate this dynamic job scheduling. So we have a number of jobs in a queue. The manager, so the queue is at the worker 0, at process 0, and there will be the requesting of jobs. Now you could try to implement this with a busy wait loop, but this might be kind of cumbersome. There is a probing, so the manager can probe the workers in a non-blocking communication, whether there is an incoming message of any of the workers. Here is the simulation. So this is interactive. And this is kind of a complicated algorithm. If you have to do this for the first time in a compiled batch environment, if you launch this on a supercomputer, chances are that, if you have done this with somehow another template of a compiled language, then good for you. But if you have to do everything from scratch, as was explained here in this lecture, then chances that this will be working from the first time are kind of minor. So doing this in an interactive environment is actually very, very beneficial. So this is again interactive supercomputing, where you get to prototype. And again, if this was your first experience thinking in parallel, you get some kind of a feel of what is going on. So here we have three jobs running with three workers and one manager. Okay, so now functions are very good. So we have a different worker function and we will have different manager functions. The worker will here, there will be as many jobs as there are workers. So the worker function will be executed only once. In a more realistic application where there are many jobs, you would have a loop, and when the job received is a terminal job, so here the job is simulated by the number of seconds that will need to be waited. If the job is a negative number, then the worker knows that there are no more jobs left. All right, so now comes the main thing. So the iProbe. So this is a very powerful construction that the message passing interface provides for us. So it's an immediate communication, a non-blocking communication. So there is the capital I here. We probe, we look for any source, and we will be able to check the result. So first of all, there is a boolean and there is a state. So if there is the boolean that is returned as true, then we know there is a message, and then we can get the source from the state. So a very non-complicated syntax that gets executed by the manager. So there is the distribution of the work. So it's the size. The size is the number of workers. And then we have the execution of the jobs. Note that the workers, they wait for different amounts of times. Here, the worker node will probe. And if okay, then it will actually print the message. The message here is actually saying that, hey, this node has finished. This process has finished. There is a sleep also in the, so this is a simulation. So this is a, so as long as the worker, the manager keeps track of the number of workers that have terminated. In order not to overwhelm the system, so this was done on a workstation, on one single workstation, and you can simulate this also on your laptop. So the earlier versions of Macs, perhaps still the current versions, actually also had distribution for MPI. So this could also be done on a laptop. And there are also MPI versions for Windows, by the way. All right, I'm done with the lecture. So we will, in this course, no longer be using MPI, unless you want to go into MPI, the wrappers for Julia. So this could be a project for learning more about Julia in this course. The exercises are mainly aimed to getting a look and feel for a message passing from within Python, the familiar environment that is Python. So thank you for watching this.